Hello, and thanks for joining the webinar. My name is Tai Kim. I work at the Automotive Market Segment team of Wind River Systems. This short presentation, I will talk about a software architecture of managing different types of computing workload for autonomous cars. We'll see different ways of partitioning hardware and applications. We'll talk about a service-oriented architecture for a vehicle electronic system, and why Wind River believes it is a very pragmatic and economic approach to build a commercial ADAS and autonomous cars. If I move on to the next slide. So before I start, just a quick introduction to Wind River Systems. We have been in embedded industry for almost 40 years, helping customers develop embedded systems. We're the market share leader of both commercial real-time operating system and commercial embedded Linux distribution. Our technology has been used in many different mission-critical systems, including airplanes, industrial control systems, telecom and medical equipment, and of course, autonomous cars, like the Audi A8 that's been selling in the market for almost 2 years right now, is running Wind River's VxWorks operating systems. And if you have been paying attention, Wind River has announced the update of VxWorks with the modern computing technologies such as C++17, Python, Rust, with very compelling networking performance, as well as improved cybersecurity related issues. So what is the characteristic, or before I go there, where do we stand in terms of the automotive industry? The car manufacturers, they call it OEMs, they're still busy improving their level 4 and level 5 autonomous systems, which will take many more years to be available in the market. But when it comes to the level 3 systems, so that includes a low-speed automated driving, such as autonomous parking, traffic and pilot that you can see in the Teslas or Audi A8 that I just mentioned, or even a highway driving autonomous systems. They're very feasible and realistic applications with a few years of lead time, and all the car manufacturers are looking at moving from a pilot program into the production. The problem is the effort of converting a prototype into a commercial product is extremely difficult to estimate, because the big difference between the lab environment with a simulated input and the real world situation, I mean, even though you knew what it takes, as we go into the program and learn more, oftentimes we realize we either underestimated or overestimated the effort of the computation power. And of course, there's myriad of technical concepts and industry standards with their benefits and disadvantages. So it becomes really difficult to make the technological selection, which makes it a little bit more important to rely on globally accepted standard with very strong industry support. And of course, the safety and security always is the critical non-functional requirements that makes everything a little bit much more difficult and costly than originally estimated or expected. So we believe the industry needs a new design approach to make this very, very challenging project into commercially viable project. So what would be the characteristics of a software platform that will enable the design and development of a commercial advanced driver assistance systems and autonomous cars? We want the system to be more software defined for a maximum flexibility. We want an open system with a very strong ecosystem versus a closed, a proprietary system architecture from a particular vendor. And we want a connectivity with safety and security. These are very generic features requirement. And how do it look like in real world? So if you look at the way the current vehicle electronic system is designed, you can see there are many ECUs, electronic control units, doing different type of work in a pre-configured manner. So here you see a various embedded system components inside the vehicle, as well as connectivity to the outside world. The components can be, under the hood, a single-purpose, deeply embedded ECUs and sensors that may run a classical AUTOSAR software as an operating system, or it can be an ADAS system that may run a complex real-time operating system, such as Windows VxWorks. Or it can be an in-vehicle infotainment system that runs a Linux or Android operating environment. And most recently, the high-performance compute gateway is becoming a very important part of the in-vehicle electronic system architecture, as it provides an interconnectivity between the different ECUs and domain controllers and within the system, as well as the connectivity to the outside world for software update and vehicle-to infrastructure communications. Now, the question is, how do we manage all those different ECUs and software-based features and functions to design a connected, automated, and electrified systems with functional safety, as well as the flexibility and expandability that is required for the next generation vehicle architecture? Obviously, the most straightforward and proven approach is to divide each application into different ECUs. So this will provide a very simplistic and robust partitioning approach based on the hardware boundary. Each ECUs will have its own CPUs, memories, I/O devices, and they will run a dedicated applications for a particular purpose. And this is a very traditional embedded system design approach, and this is what's inside in most of the vehicles selling out there today. And this is very well understood and, again, proven methodology. Now, this requires a very static workload allocation during the design and build time. And once the applications are allocated to a specific ECU, it's meant to stay there for the rest of the life cycle. And that is not a problem if the system workload is very static and predictable. But if you look at the modern vehicle design, due to the dynamic nature of complex combination of applications, the system design may have a lot of wasted hardware resources if the developers overestimated the workload too much, or it may suffer from the lack of room for additional applications or use cases. So what's happening is, as the CPUs getting more powerful and an operating system, whether it's a real-time operating system or Linux, they can handle multiple applications. We start to add more complex application combinations within a single electronic control unit based on the task scheduling and memory partitioning provided by the operating system. As we put more applications onto the single control unit, however, this will become, well, it'll help to save the hardware cost and consolidate workload. But at the same time, it introduces the risk of applications interfering with each other as they share the same operating environment, whether it's a memory management unit or the kernels and schedulers. So what the industry has moved on to provide a stronger partitioning within the same CPU is based on the hypervisor technology. And here you can see the type of hypervisor is providing a multiple operating system environment sharing same hardware resources. While it may add one more layer of complexity, in general, the modern hypervisor is a very, very thin layer of software with pretty lightweight overhead, and the benefit of hypervisor, we believe, is much bigger than the burden of added complexity and maybe small percentage of performance impact. Again, depending on how you configure the system to share the devices between the multiple operating systems. Now, if you move on and if we add a connectivity to the cloud, this is becoming a true service-oriented architecture design for the next generation transportation system. I will talk about the service-oriented architecture later, but the introduction of 5G network is making the distribution of different type of workloads to go even beyond the in-vehicle electronics, but but it can even go outside of the extra vehicle world, like cloud-based workload offloading to provide the maximum flexibility and efficiency of the computing power that's required for the autonomous driving systems. So this is an example architecture for workload management based on Wind River's Helix platform with type 1 hypervisor. You can see here a different type of guest operating system with different level of safety equipment, and some of them can be a very time sensitive real-time applications. Some of them can be an AI machine learning based more, best effort type of workload. And some of them, even Wind River Hypervisor can also support unmodified guest OS like Windows. So you can include a human machine interface applications. And then it can be a different type of layers for abstraction. And I'm not to run or combine all of these radically different type of work applications into single hardware environment. But I'm just showing you as an example. Depending on your selection of the hardware or CPU horsepower, you can consolidate and distribute workload in more flexible manner. And if you notice this white layer on top of the operating system, this is another core technology to enable more flexible workload management. And this adaptive AUTOSAR is a key foundation of the service-oriented architecture that we believe is critical piece of technology. So what is services-oriented architecture anyway? This is a distributed computing concept from the enterprise IT world, where the system consists of a set of services and applications that communicate over the network protocols. So instead of having a tight coupling between the applications and services, it's more loosely coupled, dynamically discoverable interfaces between software components. And why does it matter? For the design of automotive software, if you look at the benefits of the service-oriented architecture, these are exactly what we will be looking for to develop the next generation commercial vehicle electronics and software architecture to handle the uncertainty of the computing power demand, the rapid innovation of technology, and be able to update the software in a continuously improving manner. So the adaptive AUTOSAR that I just mentioned about 2 slides ago, we think the AUTOSAR Adaptive Platform can provide a great foundation for the service-oriented architecture for the automotive systems. I hope that most of you are familiar with this AUTOSAR partnership. But if not, this is basically an industry partnership initially driven by European automotive companies. But now I see almost 300 companies has joined the partnership. And basically, this is becoming an international de facto standard for the automotive middleware design, just like POSIX has become the international standard for the operating system environment. And one of the core values or value proposition of adaptive AUTOSAR technology is the level of abstraction it provides between the applications and the foundation computing environment. The adaptive AUTOSAR will provide a standardized way of discovering services, communication between processes, and managing execution of applications. And depending on how you define and design services applications, they can run on the same OS. They can run on different guest OSs on Hypervisor on the same hardware, or they can even run on different ECUs across the network, as I shown in the previous slide. The applications can be designed in most flexible manner without making the assumptions of static linking between services, provider and consumers, allocation of workload on specific hardware. So we believe there's a real benefit of having this flexibility of distributing different type of workload. But as you start mixing and matching various types of workload into single computing environment, what matters is to ensure a very robust partitioning between different type of workloads. in automotive term, in functional safety terminology, it is called a freedom from interference. Basically, it means the applications with different criticality should not interfere with each other. So that can mean memory protection or guaranteed execution time or end-to-end communication protection. It can happen with a single OS environment, as you can see here with the example of VxWorks time and space partitioning scheduler, or it can happen between multiple guest OS within hypervisor environment, sharing the same hardware resources. And this is a concept diagram for the next generation vehicle electronic systems based on the service-oriented architecture. And you can see here TSN, which stands for a time-sensitive networking, will become the critical part of the system design, providing a deterministic connectivity between the various computation units within the system. Here, for example, on the left-hand side, at the bottom, you see a mission-critical ADAS or autonomous driving applications. And on the right-hand side is the HMI, the human machine interface for the driver, including instrument cluster and infotainment system. And then the in-vehicle communication will be managed by high-performance compute gateway, which can also provide to the connectivity to the cloud over the 5G network interface to provide a workload distribution inside and outside the vehicle over the 5G network or in-vehicle network systems. Let me just give you a quick examples of some of these flexible workload management. Here is an example of our customer, one of our customers, Collins Aerospace, taking advantage of the legacy workload consolidation into the modern computing environment. It's very critical for aerospace industry, where the cost of certification program is extremely high. So Collins Aerospace had a huge code base for the legacy system, and they did not want to rewrite legacy software and revalidate and recertify and go through all those investment again and again. So what they've done is they use Windows Hypervisor to host a legacy workload on the legacy environment, while they keep adding different type of workload with more innovative software design. And I believe this applies equally well for automotive world, where the functional safety requirement is probably one of the most critical factors for the economic viability of the vehicle program. And the customers may not want to just blindly go through the ASIL safety allocation for the hundreds of thousands of lines of code for machine learning, image processing, AI type of work. They want to be more cautious about the cost implication. They want to be more careful about partitioning and workload distribution between different level of criticality. Now, this second example, we could not disclose the name of the customer, but it's another a workload management for an in-vehicle gateway device. So in this case, the customer was an expert of a networking equipment manufacturing, and they're coming into this automotive market with this networking application expertise. But then they also had to add more automotive type of safety critical application, functional safety, and that type of stuff. So what they've done is they've gone ahead and used a Windows Hypervisor to host their existing Linux-based networking protocols and applications. And then they had another guest OS, a VxWorks based safety guest OS to run more safety critical applications like sensor data processing or even a body control type of functions And then this is a still ongoing project, but so far things seems to be good, and they're moving along very well with the consolidation of different type of applications. In conclusion, Wind River is aware of many different ways of distributing workloads for a vehicle electronic systems. And we believe there are many very compelling software architecture that is based on modern technologies, such as Hypervisor, AUTOSAR Adaptive Platform, and a service-oriented architecture that can help design more open, flexible, and even a future-proof systems. And if you're interested in more conversation, please feel free to contact your Wind River representative. With that, thank you for your attention, and that concludes this webinar. Thank you very much.